Welcome to the solutions to the Regents Physics Dynamics problem set, problems number 29 through 31. Let's start with 29. Two trucks that appear to be identical collide on an icy road. One was originally at rest. The trucks stick together and move off at more than half the original speed of the moving truck. What can you conclude about the contents of the two trucks? We start with a before and after diagram. In our before situation, we have one truck at rest, this crappy Ford right here, and we have another truck, a nice Chevy, moving to the left. Let's start out with what the statement said up here, which says the two trucks appear to be identical. What that means in physics is that they have the same mass. So I've labeled this truck M and this truck M. We know that this truck has an initial velocity of 0 and that this truck is moving to the left with some initial velocity we don't know, and we don't need to know it because of what they're asking us. Afterward, we're told that they collide and they stick together and move off together. So it makes sense to us that they're going to collide, that they move off together to the left. And what we're going to find is what's the final velocity of this situation if the two trucks are identical. And clearly after collision here, you'd have mass M plus mass M for a total mass of 2m moving to the left with some final velocity. We make our statement of conservation of momentum, P before equals P after. What objects, if any, have momentum before they meet? Only this truck here is moving with speed VI. So we have mass M times VI equals what objects, if any, are moving after collision? Both stuck together are moving in the same line of motion. Their combined mass is 2m, and they move with final velocity VF. You can clearly see that there's an m in both terms, which cancels. And when we solve for VF, we see that VF is 1/2, or VI divided by 2, 1/2 the original speed of this truck up here. Now that's if both are identical. But this says that they move off at more than half the original speed. So what this says is that the contents, the mass of this truck, must have been greater than mass M before they collide in order for them to move off together at a speed that's greater than half the initial speed. If you do not understand this, please make sure you ask about this question in class tomorrow. We move on to number 30. We have a 0.115 kilogram hockey puck, that's its mass, moving at 35 meters per second, that's its initial velocity, strikes a 0.265 kilogram octopus, that's the octopus's mass, thrown onto the ice by an overzealous Red Wings fan. Believe it or not, the Detroit Red Wings fans actually do this after a goal is scored. The puck and the octopus stick together and slide off together. A wants you to draw a before and after diagram, and B wants you to find the final velocity of the puck-octopus combination after the collision. We start with a before and after diagram. Before collision, we have the puck of 0.115 kilograms moving at 35 meters per second. We'll draw it moving to the right here. And we're told above that the octopus initially is at rest, just sitting on the ice. His mass, 0.265 kilograms. We're told that after collision, the puck and the octopus stick together. Because they stick together, we combine their masses. So we add 0.115 and 0.265 to get a total mass of 0.380 kilograms with some final velocity that we're trying to find. We start with our conservation of momentum statement, P before equals P after. What objects, if any, have momentum before they meet? Just the puck. So we take the puck's mass and multiply by its velocity. What objects, if any, have momentum afterward? They both do, combined together for a total mass of 0.380 kilograms, at final velocity VF that we're looking for here. Do the algebra, multiply, divide by 0.380, and we get a final velocity of 10.6 meters per second. Lastly, 31. A 0.200 kilogram plastic ball moves with a velocity of 0.3 meters per second. It collides with a second plastic ball of mass 0.1 kilograms, which is moving along the same line at a speed of 0.1 meters per second. After the collision, both balls continue moving separately in the same original direction. The speed of the 0.1 kilogram ball after collision is 0.260 meters per second. A, draw a before and after diagram of this situation, and B, what is the new velocity of the 0.2 kilogram ball after collision? I think you can clearly see just by reading this question that if you don't draw a before and after diagram, it would be easy to become confused about what's going on in this question. So reread and draw a before diagram. We have a 0.2 kilogram ball moving at 0.3, collides with a second plastic ball of mass 0.1, so I've drawn it smaller, and it's moving at 0.1 meters per second. So clearly what's happening here is the larger ball moving faster catches up to and hits the smaller ball, which is traveling slower. We're told afterwards that the larger one and the smaller one continue off in the same line together, but they are not, they're separate, they're not stuck together. So our after diagram has the 0.2 moving at speed VF that we're trying to find, and the 0.1 kilogram ball moving at 0.260 meters per second. We start with our conservation momentum statement, P before equals P after. What objects, if any, have momentum before they meet? The answer, both and separate. Because of that, we take their individual momenta statements and we add them together for the total momentum before the system, before the collision by the system. Our 0.20 kilograms times 0.3 meters per second plus our 0.1 kilogram ball times 0.1 meter per second. After collision, we have our 0.1 kilogram moving at 0.260 plus our 0.2 kilogram moving at speed VF, which is what we're trying to find. Notice, just a side note here, that in both these cases we're adding the momenta together. If one of the balls had been moving in the opposite direction, we would be subtracting. But in both sides here, they're both moving in the same direction, so we're adding the momentum because they both have positive momentum. They're both moving in the same direction. We do the algebra, we multiply, then we add these two products together. Then we're going to subtract this product, and then we're going to divide by 0.20. And you should get a final velocity of 0.220 meters per second. Good practice on conservation of momentum here, and we will continue to do that as we tackle problem 32 in class tomorrow.